So in this video I'm going to have a look at the Leaving Cert Applied Maths 1998 question 2b. So we have a man who wants to row a boat across a river to reach a point on the opposite bank that is 25 meters downstream from his starting point. So let's say this is the river and the man is here and he wants to end up, let's say that's directly across from him, he wants to end up 25 meters downstream. So his overall velocity, he wants to kind of go in that direction. The river is 45 meters wide and the man can row the boat at 3.2 meters per second in still water. So watch the wording there. If that's what he can row the boat in still water, that's the velocity of the man relative to the river. So assuming the water isn't flowing, that's how quickly he can row. The river is 45 meters wide and flows uniformly at 3.6 meters per second. So the velocity of the river, VR, is 3.6 meters per second in this direction. And usually they tell you it's kind of parallel to the bank, but in this case they didn't, but you can assume that. Find the two possible directions in which the man could steer the boat. So the trick here is that you can have a different diagram for your displacements and your velocity. So the diagram I've done here already, that's displacement really. And it's showing us that the man is going to kind of follow that path that's 45 meters up and 25 meters to the right. But if I did a velocity, a vector diagram velocity, this is what it would look like. Well, the man would have to kind of go at this angle, we'd assume. So we'd call that the velocity of the man relative to the river. That's the way he'd go if the river all of a sudden stopped flowing. The river is flowing this way, so that's the velocity of the river. And then these two vectors added together would give us the velocity of the man, which would be in this direction. Now, if you look at these two diagrams, they're very different, but some things on them are the same, or some things on them we can use, something on each one we can use for the other. So, for example, if you look at this angle here, let's call it theta, that should be the same as this angle here. Why? Because this is the river bank, that's supposed to be a straight line, this is the river bank, and this is the direction the man is going to take, velocity of the man, and this is the direction the man is going to take. So that angle there is the same as this angle here. So could we get theta? Well, we can get it from our first diagram, our displacement diagram. Theta would be tan inverse of 45 over 25, which is equal to 60.95 degrees. That's theta. Now that's the same as this angle here. So the key to this question really is being able to split your diagrams into the vector one and the velocity one. Or sorry, the velocity one and the displacement one, and to see what angles are the same in each. Now in our velocity diagram we know more information. We know the velocity of the river is 3.6. We know the velocity of the man relative to the river is 3.2. And we're basically looking for the angle that the man takes when he wants to land 25 meters downstream. So we're looking for this angle here, let's call it alpha. Well, if we know theta, we have alternate angles here, we have a z, we know that that would also be theta. So from here to here is 180 degrees. So if we can use our triangle to find this angle here, let's call it gamma, then 180 minus gamma minus theta will give us alpha, which is what we're looking for. So our triangle is 3.6, 3.2 and 60.95. It's obviously not a right angle triangle, so we're looking for gamma. So we're going to use the sine rule or the cosine rule. Sine rule is probably the easiest. Sine of gamma over 3.6 equals sine of 60.95 over 3.2. That gives you sine of gamma equals 0.98 blah 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 blah. You can keep it in your calculator so you're not kind of truncating your answer. And that gives you gamma equals 79.56 degrees, or remember your unit circle, 100.43 degrees. And I know I need two angles there because in the question said the two possible directions. So this is where we get our two angles from. So now we know we have two values of gamma. So we're going to use our two values of gamma and theta to find our two values of alpha. So angle 1 will be 180 minus 79.56 minus theta, which was 60.95, and that gives us 39.49 degrees. And then angle 2 will be 180 minus 100.43 minus 60.95, because theta remains the same, which gives us 18.62 degrees. So that's part 1 answer, that's your two angles. So the maths is really easy in it, it's just the sine rule and using tan, but it's this diagram that you have to get right at the start. So don't be afraid to draw a couple of diagrams, and that kind of allows you to kind of see the bigger picture. Part 2 is find the respective crossing times. So the man has a velocity of 3.2 meters per second, and for angle 1 he's heading at an angle of 39.49 degrees against the current. So if we want to find the crossing time, we need to get the vertical distance, which we know is 45 meters, and we need to know the vertical velocity, which will be 3.2 times sine of 39.49 degrees. And then velocity is distance over time, so time will be distance divided by velocity. So 45 divided by 3.2 sine of 39.49, and that gives us 22.1 seconds. For the second angle, I won't draw it out again, but this angle basically isn't 39.49, it's going to be 18.62, so that's T1. So T2 will be the same vertical distance, which is 45, divided by 3.2 multiplied by sine of 18.62. And that gives you an answer of 44.1 seconds. So there's your two times.